Okay, so I have shared my screen. Can you see my screen now?
Yes, sir.
Okay, thanks. Okay, so before we start today's lecture, just want to mention that in the last class, so in the last lecture, I took half an hour less. Okay, so it was only for 1 hour. And then I mentioned that I will adjust this half an hour in the coming week. So maybe if you allow me, then in the next class, which is on Thursday, I can take half an hour extra. So the next class would be of 2 hours. So is it okay for you? I mean, if you have any other commitment on that day, then you can tell me. We can do it on some other day. But if not, then the next class would be from 3:30 to 5:30. So that is coming Thursday. Okay, so
Sir, I have
you tell
class on at 5 p.m.
you have a class which starts at 5 p.m.
Yes.
Okay, so then uh, like on Monday, how about on Monday? Monday also you have a class?
Yes, sir. Monday and Thursday.
Monday and Thursday class fine. Okay, so then can we start half an hour early
Yes, sir.
just for the next lecture? So instead of 3:30, we can start at 3 o'clock. If all of you agree, then the next class we can have from 3 to 5 because I want to adjust that 30 minutes somewhere. So if not, like from 5 to 5:30, then we can like prepone our next class from 3 to 5. Okay. So you let me know by the end of today's lecture, and accordingly I will schedule this class. Okay, so let's start today's lecture. Let me recall what we did in the last class. So in the last class, we introduced matrix norm, and then we define a particular kind of norm, which we called as operator norm. This is when you treat your matrix or you look at your matrix as an operator. So if A is a matrix of size m cross n, then you look at this matrix as an operator from Fn to Fn. In particular, we are looking only for, or we are considering only square matrices. So it is from Fn to Fn. And then you can consider, like you can fix two norms, one on domain and one on codomain. And using this norm, you can define an operator norm. So for simplicity, we considered the same norm on a domain as well as on codomain. And then using this norm, we define operator norm of a matrix. So if you have any vector norm on Fn, then using this vector norm, you can define a norm, which we called as operator norm. And then we looked at some examples. For example, the operator P norms we have seen or we saw or we defined in the last class. And then we also saw some examples to find out like some values for a particular norm. For example, if we have a if we try to find or if we find two norm of a diagonal matrix, operator two norm of a diagonal matrix, then it turns out that it is nothing but the the largest in absolute of diagonal entries. That is the two operator two norm of a diagonal matrix. Similarly, if we and then I also mentioned that in general also, if even if the matrix is not diagonal, there is a way to tell what is the operator two norm of that matrix, and that we will discuss when we will talk about like singular values. So that is the largest singular value. So we'll prove that, and or we will show that when we will talk about singular value decomposition. So at that time we'll show that the operator two norm of a matrix is nothing but the largest singular value. Anyway, so then we saw some other examples like operator one norm, operator infinity norm. For operator one norm, it turns out that it is nothing but is equal to the maximum column sum. Right? Similarly, for operator infinity norm, it is just the maximum row sum. So there was an exercise I gave you using a matrix norm and using an invertible matrix. You can define other norms like for a fixed matrix norm and for a fixed invertible matrix, you can define an operator norm. Sorry, you can define a matrix norm on a given on given space of matrices. All right, so now so far we have discussed several norms. We also know several ways to like to define new norms. So far we have like a family of norms. So in today's class, I will talk about one quantity that is not a norm on space of matrices, but it is closely related to the norm. So this we will call as spectral radius. So what is a spectral radius? Spectral radius is nothing but the largest eigenvalue in modulus. Okay, so largest eigenvalue in modulus, that we will call as a spectral radius, and we'll see that this spectral radius is not like itself is not a norm, but it is closely related to a norm. In fact, we will show that it is the greatest lower bound for the values of all matrix norms for a fixed matrix. So I'll mention what do I mean by that. But before I start defining spectral radius and look at the properties, if let me recall that at the before starting these norms, as a motivation, we wanted to answer one of the question that when does this kind of like series formulation make sense for a given matrix. So for example, when we have a real number or a complex number z, then we know when such a series converges, right? But if I replace this z with a matrix A, then still this is a formulation, but we need to see when such a formulation is valid. So basically, we want to see when such a series of matrices, it is in fact a power series in matrices, such a series converges, that we wanted to answer. So for example, can we talk about like matrix exponential, right? Or can we define like cos A, sin A, this kind of thing? So whatever we have like for real or complex numbers, can we have similar like analog for matrices also? So this we wanted to answer, and that's how we felt that okay, we possibly need to have some kind of measure for the size of a matrix, and this is what we are trying to do in the previous lectures. So in today's lecture, our aim is to answer this, and we will try to conclude matrix norm, this section on norms and matrix norm today. And in the next class, we will start matrix factorization. So this is the plan for today's lecture. So if you have any doubt at any place, you can stop me and you can ask your doubts. Okay, so let us start by defining spectral radius. Okay, so the spectral radius, what do I mean by that? So if suppose I have a matrix A, which is of size n cross n over F. Okay, or for simplicity, let us fix it C. F is C here. So then, and let me denote this as the set of all eigenvalues. This lambda A, this is the set of uh, eigenvalues of A. Okay, so this is the collection of all eigenvalues of A. Then the spectral radius of A, which is denoted by this rho A, this is the standard notation for the spectral radius of a matrix. So what is this? This rho A is nothing but the maximum, the largest eigenvalue in modulus. So that means you take the maximum of mod lambda, where lambda is varying over all eigenvalues. Okay, so this is called the spectral radius of A. Now, as I mentioned, this for every matrix A, you can talk about this. So basically, you can define a function from this rho is a function from set of matrices to R. Like it is defined this way. It is the largest modulus, largest eigenvalue in modulus. So this is a function, but this function is not a not a matrix norm. This is not a norm, not actually a norm. Forget about matrix norm. This is not, in fact, a vector norm. Why this is not a vector norm? Because you can look at, actually you can construct any example, but let's just for simplicity, let us look at this example where what I want to say is that row A, this function is not a norm. Why? Because if you look at this matrix, or let us look at what is the spectral radius of this. So what is the spectral radius of this matrix? What is the spectral radius of this matrix?
0.
This is 0, right? But it is but it cannot happen if it is a norm. So it's a non-zero matrix whose value is 0. So this cannot happen for a norm, and therefore this is not a norm. This is not a norm, but it is this function or the spectral radius of a matrix is closely related to a norm. Closely related to a norm in the sense that if so, let me first prove a result, and then I will show that this is actually spectral radius is the greatest lower bound, or you can say this that this is the infimum over all infimum of the values of all matrix norms of A when that norm is evaluated for this matrix A. So what I'm saying is that for a given matrix A, rho A is nothing but the infimum of this quantity, that means the value of norm of A over all matrix norm, all possible norm on the space of matrices. So you can say that this is actually a greatest lower bound for all such values. So it is not a norm, but it is closely related. And this is one of the things which will give us a characterization to define or to say when a power series in matrix is convergent, or when such a formulation like makes sense for matrices. Okay, so this is what we will try to do. But one thing is very easy to like observe. I will write it as a result that if for any matrix norm, so if suppose this is a matrix norm, this is a matrix norm on space of matrices, then so let me say, let's say on this, then for each A, whatever matrix I take A in this, rho A is less than equal to norm of A. So this is true for any matrix norm. So basically now you can see that whatever I was saying, clearly this rho A gives a lower bound for that set, but we will show that it is the greatest lower bound. So why this result is true? So this is not difficult to observe. So what we have to show? We have to show that rho A is less than equal to matrix norm of A. Okay. So we know that rho A is what? Rho A is the model is the largest in modulus, right? Largest eigenvalue in modulus. So suppose that lambda is an eigenvalue of A. Any eigenvalue, okay? Lambda is an eigenvalue of A. What does it mean? This means that there exists x not 0 in Cn such that Ax equal to lambda x, right? Now what I can do here, I can construct, let's say, a set, let me call it Y. What is this set? This is the set, this is a matrix, this Y is a matrix where it's an n cross n matrix where each column is equal to this x. Okay. Now look at what is this? Ay equal to lambda times y. Not Ay equal to lambda times y, but what I'm saying is that when you do this ay, when you operate a or when you multiply a from left hand side to this y, then what you will get, it would be like a, it is this kind of thing, right? X and so on up to x. But then if you multiply column wise, the first column would be ax, the second column would be ax, and so on. But you know that ax is just lambda x, so it is this. But then you know that you can take lambda out, and then this is just the matrix y. So basically we know that ay is equal to lambda y from here. So what does it mean? This implies that if I take both sides, if I take the matrix norm both sides, then it would be like mod lambda norm y equal to norm of ay. But then this norm is a matrix norm, so it satisfies submultiplicativity. So it would be less than equal to norm a, norm y, right? But then what can we say from here? Can you tell me what we can say from here? So what can we conclude from here?
So spectral radius is less than the norm of A.
Why?
Because spectral radius is always greater than the modulus of each eigenvalues.
Okay, so
And from here we can see that mod of lambda into norm of y is less than, always less than equal to that.
yeah, so from here you can say that mod lambda is less than equal to norm a. Why this? Because norm of y is a non-zero number, because y is non-zero. And why this matrix y is non-zero? Because x is non-zero. So this is fine, but this is true for all lambda, for all eigenvalue lambda in this set, because we have started with an arbitrary eigenvalue lambda. So if this is true for all eigenvalue, then it is also true for the maximum. So that means from here we can say that rho of A is less than equal to norm A. So spectral radius is always less than equal to norm of A, where norm is the matrix norm. So for any matrix norm, this inequality is satisfied. But then you can say why you are, so you can see here why I have mentioned matrix norm. Why not vector norm? Because here you can see that I have used the sum multiplicativity. So if the matrix norm is not a, if this norm is not a matrix norm, and in place of, suppose that in place of matrix norm, if I take a vector norm, which is not a matrix norm, then for that norm, this inequality may not be true or need not be true. Why? For example, you can take this example. So if you take, let's say, so what I'm giving you next, this is an example of a vector norm. Let's say this on this, such that there exists a matrix A with norm A less than rho of A. So what I'm saying is that this matrix inequality, whatever we have established so far for matrix norm, that is not true, or that need not be true when the norm is a vector norm and not a matrix norm. Okay. Now, this constructing such an example is not difficult, because we already know at least one norm. I have already given you example of one norm, which is a vector norm but not a matrix norm. Can you recall what is that norm? We have already seen one example of a norm on space of matrices, which is a vector norm but not a matrix norm.
Maximum of all entries.
Yeah, it's the infinity. Yeah, it's the L infinity like norm. So what was that? It is this one. It's the max of all entries. You can check that this is a vector norm, but not a matrix norm. Now for this norm, this is a vector norm. If you take this example, okay, now can you tell me what would be the spectral radius of A?
2.
Spectral radius is 2. And what is the infinity norm?
1.
It is 1. So here is an example where we can say that this norm is strictly less than spectral radius. So in this result is true, or this is true, or this holds when the norm is a matrix norm. Okay. So as I mentioned that this spectral radius is not a norm, but it is closely related to the norm. So we have already seen that it, for a matrix norm, it always gives us a lower bound. Here you can see, right? Lower bound. But in fact, we can show that this lower bound is the greatest lower bound for such a set. So what I'm saying is the following. So next, what I'm proving? Next, what I'm proving here is the following. So matrix or spectral radius of a matrix is nothing but the infimum of all infimum of all these values, norm A, where this norm is a matrix norm. Okay. So what is the meaning of this? In other words, or if you want to write it more precisely, then what you can say, or in other words, you want to say that if A is a matrix, A is a given matrix, and epsilon greater than 0, then, so can you tell me how to prove that? How to prove that rho of A is equal to infimum of this set? Can you tell me mathematical way to prove this? What we know that for any given, what we know from the previous result, we know that for any given matrix norm, and A is any matrix, fixed matrix, then this is always greater than equal to this. Now we want to prove that rho of A is equal to this infimum. Now can you tell me a way to prove, mathematical way to prove this? How to show that this is the greatest lower bound for this? Yes. Can you tell me this? Anyone? So this is simply we want to prove infimum of we want to find infimum of a set. We already have a lower bound. And we want to show that the lower bound is the greatest lower bound. It's a simple question, right? To find infimum of a set. How to show that that lower bound is actually infimum? Tell me how to show that this lower bound. So we already know that rho A gives a lower bound for this set. Okay, this gives us a lower bound less than equal to this set. This is a lower bound. We know from the previous result. But why this is the greatest lower bound? That means this is the infimum of this set. I'm not saying you give me a proof. I'm just saying how to prove this. Can you give me some idea, or at least a way, standard way to prove that a lower bound is actually an infimum, is the greatest lower bound? How to check by definition?
So if I just take like rho A plus epsilon, then I'm able to find one norm such that norm of A will be like less than Rho A plus
Right,
epsilon.
exactly. This is the way, right? This is how we do. So if A is a matrix and epsilon is any positive number, then I will show that there exists a norm, there exists a matrix norm. Let's say this one, such that this matrix norm of A is less than equal to rho A plus epsilon, because we already know that rho A is a lower bound. So whatever epsilon I take, if I add this epsilon to rho A, then this cannot be a lower bound. So what does it mean? It means that there exists a matrix norm for which this inequality holds. Okay, so this is what we are trying to do next. Okay, so before I start the proof, let me recall one thing. I am assuming that you know this thing, but anyway, in the next class, I will state this result and give you a short, brief proof also, or at least the idea of that result. It is the Schur's lemma. I have already talked about this in 101 and also 104. You have learned this in 101, in MTL 104 also, and also MSc students might have learned this in MTL 502. So what is Schur's lemma? Can you tell me? What is Schur's lemma? Can you recall what is Schur's lemma? Okay, so it says that if you have a matrix A, let's say n cross n matrix A, then you can find a unitary matrix U such that U star AU is equal to some upper triangular matrix. This is the Schur's lemma. This you can do for any given matrix A. There exists such a unitary matrix such that A can be upper triangularized, or you can say that every complex matrix, square complex matrix, is similar to or unitary similar to a to an upper triangular matrix. Okay, so this result I will require for this proof. So recall Schur's lemma. So what is that? So by Schur's lemma, there exists U. So a matrix A is given to us. So there exists U unitary of size n cross n. So this is unitary such that A is equal to U star TU, where T is upper triangular. Okay. So this is because of Schur's lemma. Anyway, we will recall this decomposition again, maybe in the next class. But I will need this result for this proof. So let us suppose that for this A, I have this matrix U such that U star TU is A, where T is the upper triangular matrix. So this A is unitary similar to T. Now what I have to find? I have to find a matrix norm. Okay. So now what I will do here, let me tell you what is the plan. I will find a norm. Okay. So how would I define this norm? I would define this norm using some well-known matrix norm. For example, I'll choose this norm accordingly, but my plan is to do it in this do the following, that I will somehow show or generate a matrix norm this by using some invertible matrix. So what I will do, I will define a norm in this way. Some matrix here and then S inverse, and this is some non matrix norm. So we know that for any matrix norm, so if this is a non matrix norm and S is an invertible matrix, then this is again this function defines a matrix norm. This we have seen in the previous class, right? So I am trying to find such a matrix S and this infinity norm. And I'll do it in such a way that this inequality is satisfied. All right. So let us see how we can do that. So what I'm doing here, I will construct a diagonal matrix D, which is of this form T square. So this is a diagonal matrix. So maybe I should write it in this way. So D is a diagonal matrix where at the diagonal I have T square, T cube, and so on to T to the power n, where T is some positive number. Okay, where T is some positive real number. And then with this T, with this D, I will compute this dt D inverse. Okay. So let us assume that the entries of T are of the form Tij. It's a upper triangular matrix. So assume that entries of T are of this form. Now, can you tell me what would be this dt D inverse? It would again be an upper triangular matrix, but what would be at the diagonal? So diagonal would be, if suppose I denote lambda1 to lambda n as the eigenvalues of A. So let's say if T is of the form this, let's say lambda1 to lambda n, where this lambda I is actually Tii, and then these entries are 0 because this is an upper triangular matrix, and here I have these Tij's entries, okay, in the upper triangular part. So what would be dt D inverse? It would be lambda1, lambda2, and so on up to lambda n. Then 1 2 entry would be T inverse. It's simple multiplication. You just multiply T. So you just look at dt D inverse. It would be this one, T12, then T minus 2, T13, and so on. And this is T to the power minus n plus 1, T1n. And similarly, you can obtain these entries also. Okay, T to the power minus 1, Tn minus 1n. And these entries are 0. The lower triangular part is 0. Okay. So what I'm trying to do actually here, if I now you look at this, in every term here in the upper triangular part, I have T inverse. Okay. So if I choose this T and this D is defined using this T, right? So this T is greater than 0, any real number, positive real number. So if this T is very large, if this T I choose large enough, then you can see that the sum of these entries, if you look at here, that can be made arbitrarily small if I choose T large enough, right? Now this will give us a way to define matrix norm, which we want here. So for what you can say here, that for large T, the sum of the absolute values of off-diagonal entries of dt D inverse is less than epsilon. If I choose T large enough, so what I can say that for large T, the sum of all the absolute values of the off-diagonal entries of dt D inverse is less than epsilon. Okay. Or in particular, what you can say, in particular, you can say that if I look at the operator T norm of the operator 1 norm of this dt D inverse. So you tell me what it would be, or what we can say. Operator 1 norm is the maximum column sum. And here what for large T we can say that the sum of all these entries is less than epsilon. So definitely if I take the column sum here, this is the maximum column sum. So you just take the column sum and take the maximum of it, that would be your one norm. So what we can say from here, that is definitely going to be less than equal to rho a plus epsilon. Why this is? Because the diagonal entries are nothing but the eigenvalues. So if you look at the columns, this matrix one norm, then it is the sum of the diagonal entries. You have to choose the maximum. So let's say maximum is appearing in some column, let's say jth column. Then it is the entries below the diagonal in that column are all 0. And then you know that the sum would be mod of lambda j plus the sum of the entries above this entry in this column. But we know that sum of all the off diagonal entries is less than epsilon, so that is definitely less than epsilon. And then mod lambda, which is the largest, or which may not be largest, but that is also definitely going to be less than equal to rho a, which is the largest eigenvalue in modulus. So definitely one norm of this is less than equal to rho a plus epsilon for large T. Right? So remember what is one norm here? It is maximum column sum. So you can verify that for large D, it is possible to find a D such that this is true. So for such a T, we can do the following. We can define now a function or a norm on this space of matrices. So how to define this norm? So now can you tell me, using this information, how to define this norm such that norm of A is less than equal to rho A plus epsilon. This A is the given A. So remember, for this matrix A, we are trying to find a norm such that norm of A is less than equal to rho A plus epsilon. What we know so far, we know that there is one norm, operator one norm of this matrix is always less than equal to rho A plus epsilon. So somehow I should define this function in such a way that I can use this information. Now you tell me how to define this function so that when I evaluate this function at A, then it should satisfy this thing. Or you can say that when I evaluate this function A, then this function value should be equal to this one. Then I can immediately say that this is less than equal to rho A plus epsilon. Okay. So can you give me some idea how to do that? So if I take any, so I need to define this function. So if I take any matrix B, then what should be its value? Can you tell me how to define this function? What should be the value of B under this function? So what about this? So we already know this, right? So what we want that when I evaluate A on this function,
du like again like
yeah, tell me
du
what?
like
Du,
u b u star d inverse.
right, exactly. This is the one norm. Because we already know that such D is an invertible matrix because T is greater than 0, D is diagonal. D is invertible, U is unitary, so it is invertible, so their product is invertible. So this is an invertible matrix here, and then we have a matrix norm. So such a function always defines a norm. So this function here is the norm. And what this function satisfy? So for large T, so if T is large enough, we can always choose it according to the entries of the upper triangular matrix T. If T is large enough, then this norm satisfies that the value of A under this norm is just DUA U star D inverse. But then you know what is this? this is just equal to D, T D inverse. But we know that D T D inverse one norm is less than equal to rho A plus epsilon. Okay. So this gives us a norm such that the norm of A is less than equal to rho A plus epsilon. So we can say that spectral radius is the greatest lower bound of the values of matrix norm of A under any matrix norm. Okay. Now this is fine. Using this information, our ultimate goal is to give us a or to find a criteria under which we can say that series in matrices is convergent, or maybe infinite series of matrices makes sense. Right? This is what we are trying to do. So now you can, let me give you one exercise here, which is very easy to verify. That if A is a matrix, A is an n cross n matrix over C, and this is a matrix norm on this space of matrices. Now, if norm of A is less than 1, strictly less than 1, then you can easily tell, or you can quickly tell, that I minus A is invertible. Can you see this? Why this is true? Can you give me some hint why this is true? Or some idea can you give? So we need to show that I minus A is invertible. So if I show that all the eigenvalues of I minus A are non-zero, then definitely it is invertible, right? So can you see that all the eigenvalues of I minus A are non-zero by this information that norm of A is less than 1? So what you are given? You are given norm of A less than 1, right? But then this implies that spectral radius of A is less than 1, because spectral radius is always less than equal to norm A, because norm is the matrix norm. So this is always less than 1. But then using this, you can say that, so what is the relation between eigenvalues of I minus A and the eigenvalues of A? That relation you can find and you can quickly tell. So this is the hint that you can use in order to show that I minus A is invertible. Okay. Let me give you one more exercise. These are simple exercise. Like I have already mentioned the hint here. Just show the relation between eigenvalues of I minus A and eigenvalues of A. This relation will give you, using the fact that all the eigenvalues of A are less than 1, this will imply that eigenvalues of I minus A are non-zero, and therefore it is invertible. Similarly, let me first tell you what is a diagonally dominant matrix, and then I will give you an exercise for that also. So before I give you this exercise, let me recall what is a diagonally dominant matrix. So let us define what is a diagonally dominant matrix. So if A is an n cross n matrix, then A is called strictly diagonally dominant if for each j the jth diagonal entry in modulus is greater than the sum of the remaining entry in the jth column. So that means in a column, you look at the jth diagonal entry, that means the jth entry, and if that entry is greater than the sum of the remaining entries here, then this matrix, and this is true for each j, for every column, then that matrix is called strictly diagonally dominant. Sometimes there is so here I have mentioned strictly diagonally dominant, but sometimes this word is also used, diagonally dominant. But here we will like differentiate this terminology by saying that it is called diagonally dominant if this is, if equality is also allowed, like we have this term is greater than equal to. But it is called strictly diagonally dominant if this inequality is strict. All right, and you, with this, again, whatever we have done so far, you can, using that information, you can prove the following exercise again, that if a matrix is strictly diagonally dominant, then A is invertible. Okay, so every strictly diagonally dominant matrix is invertible. Okay, so this again, this is not difficult to prove. You try to use the fact that whatever we have done, so try to use this previous result, that row A. You need to think about how you can do that. So you can use the fact that you can use the previous exercise here, this one, and you can use the fact that for any matrix norm, row A is less than equal to norm A. So using this, you can prove this one. Okay. All right. So this is also an exercise for you. Okay. So now, if suppose we want to, what was our ultimate goal here, or in today's lecture? Our goal is to show or to say something about this kind of terms, right? We want to say that when such an infinite series in matrices, or you can say the power series in matrices, makes sense. Okay, so that means when this kind of series is convergent, we in other words, we are trying to say, or we are trying to characterize matrices A such that this a to the power k is going towards 0 when k goes to 0, goes to infinity. So we are trying to do something like this. So next we will characterize matrices for which this thing is. So that means every entry of a to the power k is going towards 0 or converging towards 0 when k tends to infinity. Okay. So this is what we are trying to do next. Okay, so let me write a result here. So in this result itself, it will be clear when we can say that a to the power k is tending towards 0. So suppose that we have a matrix A of size n cross n. Now, if for this matrix, if there exists a matrix norm, any matrix norm, if there exists a matrix norm, let's say this one, such that norm of A or the value of A under this norm is less than 1, then we can say that as limit, or we can say that limit of a to the power k when k tends to infinity is 0. So what is the meaning of this? That all the entries of a to the power k tend to 0 as k tends to infinity. Okay, so what is the meaning of this? That That is all the entries of a to the power k tend to 0 when k tends to infinity. Okay, so now you can see that this result gives you a way when you can say that the entries of a are going towards 0. So you just need to find a matrix norm whose such that the value of a under that norm is less than 1. So if you can find a matrix norm such that norm of a is less than 1, then you can say any matrix norm for which this is satisfied, then you are done. And why this is just an observation. I have written this as a result. Why this is very immediate to see? Because what is given? Given is that if so the given condition is that if there exists a norm such that this, so this is given. So we are given a matrix norm such that norm of a is less than 1, right? So we know that if norm of a is less than 1, then clearly what we can say, if norm of a is less than 1, what can we say about norm of ak? Can you tell me what would be norm of ak here? Using the fact that this norm is a matrix norm, so clearly this using the sum multiplicativity, we can say that this is less than equal to norm a to the power k, right? But since now this is just a real number whose value is less than 1, so we can say that this thing tends to 0 as k tends to infinity, right? So in other words, you can say now that this implies that if norm of ak is going towards 0, that means ak goes to 0 with respect to this given norm. With respect to this norm, ak tends to 0. But since all norms all vector norms on a finite dimension vector space are equivalent, this space of matrices, this is also finite dimensional. And here a norm is given which is a matrix norm. So matrix norm is also a vector norm. So all the vector norms are equivalent, right, on this space. So in particular, you can say that if this is going towards 0 for this norm, then this ak goes to 0, goes towards 0 with respect to any vector norm, because we know that any two vector norms are equivalent on a finite dimensional vector space. Or in particular, you can say that this ak goes to 0 with respect to this infinity norm, which is the max of all entries. So if in other words, if the max of all entries goes towards 0, that means every entry of a to the power k is going towards 0 when k tends to infinity, right? So therefore, you can say that when norm of a is less than 1 for any matrix norm, then limit k tends to infinity, a to the power k is equal to 0. Anyways, this is just an observation. But then we can give for a matrix. So this depends, whatever I have mentioned here. This depends on a matrix norm. So this, although I have given you one way to say when this kind of thing makes sense, when we can say that a to the power k is going towards 0. So this result says that, okay, you can find, if you can find a matrix norm such that norm of a is less than 1, then you can say such a thing. But it would be good to have a criteria on the matrix itself. Okay, so if I can say that for a given matrix A, if this matrix satisfies something, then or if we can say that if we can give a criteria on this matrix itself instead of the norm, then it would be good to have such a thing, because then just by looking at the matrix, I will check that property. If that property is satisfied, I will quickly say that ak is going towards 0 when k tends to infinity. So in the next result, we will do that. So it says that it's a similar result like this, but instead of norm of A, I will say that if the spectral radius of A is less than 1, then limit k tends to infinity, a to the power k is 0. And the other side is also true. So it is an if and only if result. So basically the next result gives you a criteria to say when limit k tends to infinity, a to the power k is 0. Okay, you understand what I'm saying? So what I'm going to do here, so this is the main thing. This result gives you a criteria to say when a to the power k tends to 0. So if A is any matrix over C, then you can show that limit k tends to infinity, a to the power k is 0, if and only if the spectral radius of A is less than 1. So this is if and only if. So this is very interesting because now we have the condition on matrix A itself. So if we have a matrix A, then we can quickly look at the spectral radius, that means the largest eigenvalue in modulus. If that is less than 1, then I can say that this term goes towards 0. So we have a criteria for saying when the sequence a to the power k tends to 0. All right. So why this is true? The proof is not difficult. Proof is in fact very easy because we already have whatever is required for this proof. So this is if and only if. So we have to prove both the direction. So let us prove the if direction first. Okay. Now can you tell me how? Just use the basic linear algebra and try to say why this if direction is true. So we have to assume, so let us assume that a to the power k tends to 0 as k tends to infinity. This is given to us. Now we have to show that rho a is less than 1. Why this is? So rho a is less than 1. Why this is true?
Because the spectral radius of zero matrix is 0, if and if rho a will be greater than 1, then this will not satisfy.
But the spectral radius of a zero matrix, so where this zero matrix is coming from?
So since it is given that a power k tends to 0.
But it is tending towards 0. So whatever you are saying, that would be true for a to the power k when k is large enough. But now you have to show that spectral radius of A is less than 1. So basically what you do, spectral radius means what? You just have to show that the largest eigenvalue in modulus is less than 1. So if you show that every eigenvalue is less than 1, or modulus of every eigenvalue is less than 1, then its spectral radius is also less than 1. So you take let me give you a
It's
start.
like similar to a diagonal matrix, and then through them.
A is, yeah, can you come again? Can you please repeat your argument?
So like we are in complex numbers, so like and so A will be like similar to a diagonal matrix, and then AK will be like A raised power k will be something P times D raised power of K P inverse.
Yeah, but first of all, not every matrix, every complex matrix is diagonalizable or similar to a diagonal matrix.
Yeah.
That is not true. Probably whatever you are saying that may be true for a class of matrices, that means the diagonalizable matrices. But here we haven't assumed anything on A. We are just saying that A is any matrix such that a to the power k goes towards 0. So I'm giving you a start. Let's say if lambda is an eigenvalue of A, then what do I mean by that? Just tell me, when lambda is an eigenvalue, when do we say lambda is an eigenvalue?
Ax equal to lambda x from
Yeah, so then if there, so lambda is an eigenvalue means if there exists x non-zero such that ax equal to lambda x, this is fine. But I have given that a to the power k goes towards 0. So I need to find some formulation in a to the power k. So what I can say from here? Can you tell me? From this, what I can say? If ax equal to lambda x, then
A power
what would be? Yes, a to the power k x is equal to
lambda power kx.
lambda to the power kx. This is because we have a relation between eigenvalues of a and a square, or any power of a. But what is given to us? A to the power k goes towards 0. So what we can say from here? From here, we can say that lambda k x goes towards 0 as k tends to infinity, because a to the power k goes towards 0, right? But if lambda k x goes towards 0, then what is the meaning of this? What is the meaning of this? X is a non-zero number, and here lambda k x goes towards 0. Can we say here from here that lambda k goes to 0 as k tends to infinity? Right?
Yes, sir.
But then lambda is just a scalar. When this kind of condition, this kind of thing is true, what does it imply?
Lambda is less than 1.
Mod lambda is less than 1, right? So this is true for any eigenvalue lambda. So this implies that rho of a is less than equal to, or less than, sorry, strictly less than, not less than equal to, strictly less than 1. Okay, so if direction is very straightforward. Now let us look at the only if direction. Now let rho a is less than 1. Okay. Now what can you say? So we have already done a result here. We have already proved one result, that rho a is the least upper bound. And if we have this kind of condition, what can we say? Can we say from here that there exists some matrix norm, such that norm A is less than 1? Can we say this? From here, can we say that there exists a matrix norm such that norm A is less than 1?
Yes, sir.
Yes, because we know that rho A is
Yeah.
the greatest lower bound. Using that property, I know that if I take rho A plus epsilon, so if I take any rho A epsilon, which is less than 1, so because rho A is less than 1, so I can always find an epsilon greater than 0, such that rho A plus epsilon also remains less than 1. But then we already know from the previous result, one of the results we proved today in today's class, that there exists a norm such that norm of A is less than this. So clearly norm of A is less than 1. So from here, we know that there exists some matrix norm such that norm of A is less than 1. But then because of the previous result here, you can see if norm of A is less than 1, then clearly limit k tends to infinity, a to the power k is 0. So this implies that a to the power k tends to 0. And we are done. So the result is very straightforward, provided we know these simple inequalities. Okay. Now, there is one result which I'm not going to prove. It is very standard and you can find it in any textbook. It is called Gelfand formula. What it says, so it's just for your information. It is not going to use in the next results. So it is just for your information. I'm giving you this result. The proof is also not difficult, but I don't want to spend time on this. It's a constructive proof. So it is called the Gelfand's formula. So what it says that if we have a matrix norm, it's any matrix norm, okay? Any matrix norm on this, okay? Then you can actually show that for any matrix A, the spectral radius is actually equal to limit k tends to infinity this. So this is very standard result, but we are not going to use this. This is just for your information that in fact we can find for any given matrix A using the norm, any matrix norm, we can tell what is the spectral radius of A. So without calculating the eigenvalues, so what is the use of this result? This result says that this is true for any matrix norm. So if somehow finding matrix norm of a matrix is easy, for example, in some cases, matrix norm is just, for example, the largest column sum or largest row sum. So if you just take some simple matrix norm, that means for which finding matrix norm is easy, and if we just find out the this limit here in the right hand side, then this formula says that this limit is actually equal to the largest eigenvalue of A in modulus. So that means without actually finding the eigenvalues, we can tell what is the spectral radius using this result. Okay. All right. So let me. So with this preparation, now we can come to our main question, which we wanted to answer. But before that, let me just recall from your basic real analysis that so for example, an infinite series of real or complex number converges if it is absolutely convergent. So you know that if we have like this, if suppose AK is a sequence of real or complex numbers, then if this is absolutely convergent, so absolutely convergent implies that this series is convergent, right? This we know. So absolute convergence implies convergence. So for any infinite series of real or complex numbers, if it is absolutely convergent, then it implies that the series is convergent. So absolute convergence implies convergence. But if you go from real or complex numbers to some norm space where we have a way to replace this modulus, that means we replace this modulus by norm, then also this kind of result follows. So you can say that this fact extends to any finite dimensional norm space. So that means what I'm saying, that if V is any finite dimensional norm linear space, or that means a vector space with a norm, so that is it is a norm space. So if we have a finite dimensional norm space, and in that norm space, if this is convergent, that means this is the series of vectors. Okay, if this is convergent, then this implies that this series is convergent. This is also just an natural extension from here to any norm space, because there we have a way to measure the length using the norm, and this is true. This is true for any vector space where we can have a norm. So any finite dimension vector space with a norm, we can say this thing. Okay. So basically what I'm saying, that this idea of, or you can say the questions of convergence of infinite sequence or series of matrices also can be treated using the vector norms. Okay. So here I just said that V is a vector space with a norm. And there we have a way to measure to say when such a sequence is, or such a series is convergent. If this is convergent, then we say that this series is convergent. So space of matrices itself is a vector space, right? So if we take any vector norm on this, then we can say these things, right? So if we are talking about sequence of matrices, then we know when such a, or we know the notion of convergence of such a series, because this is just can be treated as a vector, or this space of matrices can be treated simply as a vector space. And if this is a norm, then if this series is convergent, then we can say that this series is convergent. So for matrices also there is nothing new if we simply talk about convergence in this sense. But there is one extra thing for matrices. You know, in general vector space, we don't have this notion of multiplication. But for the matrices, we have multiplications defined, natural multiplication defined, and therefore we can talk about power series, right? So for example, what I'm saying is that if we simply talk about convergence, simple convergence of series, then we can just use whatever we know from finite dimensional norm linear space. That is fine. But in fact, we have something extra for matrices. This is the power series. That means this kind of series, at least we can define. We will see whether such a series makes sense or not, but we can talk about this kind of series for matrices. We cannot talk about this kind of series for vectors. For vectors, this kind of thing is not defined, right? For a vector, we cannot take the power. This multiplication is not defined. But for matrices, it is defined. And therefore, we can talk about when such a series convergent. So it is actually a power series in matrices. So this is what is makes this matrix norm and space of matrices like something extra. So now in the next result, I'm giving you a more general way, or this result gives you a way to say, to answer all the questions we had imposed at the beginning. So I will first state this result, then we will answer the questions we had asked at the beginning, and then I will come back to the proof of this result. Okay. So let us first understand. This result is very easy, but this is very useful. You will see why this is useful. So let me state the result. What this result says, this says that suppose this ak j to the power k equal to 0 to infinity, this is a power series. This is a power series, simple power series where ak belongs to, so this is in the complex number. Okay. So suppose that this power series has radius of convergence r. Okay. So suppose we have a power series which has a radius of convergence r. Okay. Then the matrix valued series, then with the same coefficients ak, now I am replacing z by this a. A is a matrix. Okay. Then this series, this matrix valued series ak a to the power k converges for every matrix A of size n cross n with rho A less than r, and diverges when rho A is greater than r. So this result is very useful now. You can see why this is useful, because this tells you when such a series makes sense. Such a series is convergent if rho A is less than r, and diverges if the spectral radius is greater than r. But what is this r? This r is nothing but the radius of convergence of this power series. And this is a simple power series of real numbers or complex number. This we know when this power series converges. So here we can actually tell when such a series makes sense. For example, so before I give you this proof, you can look at, or you can tell me when such a series, when this is this or whether this is a valid thing to write or not. So what I'm saying, so I'm defining exponential of A of a matrix using this series. So the limit of this series I'm calling as exponential of A. You can check using this result that this series is this function, whatever I have defined here for a matrix A, this is a well-defined function. So this is actually defines exponential of a matrix. And why this is true? Because of the previous result. If you look at this series, what is the corresponding series here in scalars? It would be this one. Now you can tell me what would be the radius of convergence of this? This is simply e to the power z, series of e to the power z, right? But when does such a series converges? What is the radius of convergence of this series? Can you tell me? Can you tell me what would be the radius of convergence of this?
Infinite.
Infinite. So for any matrix A, any square matrix A, this matrix exponential is defined. Now you can see here. So this makes sense. So one of the answer we have already received, or we have already obtained. Okay. Similarly, the same way you can answer when this cos of A, or let's say sine of A, this function makes sense, right? At least you can define cos of a matrix, sine of a matrix. So the question is, okay, you can define, but the question is for what A is this defined? Similarly, for what A sine of A is defined? And in fact, you can say that for all A, you can actually define cos A and sine A using the same, what would be the cos of X? This series you can use and then find out the radius of convergence of that, and correspondingly you can define cos of A. Similarly, you can use the power series of sine X and you can define sine of A, right? So now you can see that whatever questions we had imposed, this kind of thing makes sense provided we know the radius of convergence R here. All right. So let us prove this. So I have 10 minutes, so I'll try to prove this quickly. This result is not difficult to prove. So this is like, suppose that we have to show that this series is convergent, or this series converges when spectral radius is less than R, and it is diverges and this is greater than R. So first, suppose that spectral radius for a given matrix A, spectral radius is less than R. So this is the first case value. Now we know if the spectral radius is less than R, then so I don't have much time, so I will just write the proof. So if rho A is less than R, then we know that there exists a matrix norm, right? There exists a matrix norm, this such that on a space of matrices such that norm of A is less than R. Using the same idea, or using the same argument, why such a norm exists, because rho A is the greatest lower bound. Using that result, we can find a norm such that norm of A is less than R, matrix norm. But then what would be this? AK, A to the power K. So if let's say k equal to 0 to n for any natural number n, can you tell me what is this one? Using the fact that we have a matrix norm such that this satisfies. So this quantity is definitely using the submultiplicativity of the norm. This quantity is less than equal to k equal to 0 to n mod ak norm a to the power k. Is it okay? Right, this inequality, because this norm is a matrix norm. So using the submultiplicativity for any n natural number n, this is fine. But then we know that this norm a here is less than 1. Norm a is less than 1. So this series converges because of the given thing that this has radius of conversion r. So what we know, so this implies that this series converges here because now this is a series of scalars. So if this converges implies the left hand side this also converges. So this implies that maybe I'll just write this converges. This implies that this also converges. But if this is convergent, the left hand side is convergent, this implies that AK by definition this converges. Okay, so clearly whenever spectral radius is less than r, this series is convergent. But similarly, you can show that if rho a is greater than r, then this series is divergent. Why this is? Because if rho a is greater than r, what does it mean? It means that there exists an eigenvalue lambda such that mod of lambda is greater than r, right? So such that mod of lambda is greater than r, because the spectral radius is nothing but the largest eigenvalue in modulus. But if lambda is an eigenvalue means what? There exists an x non-zero such that ax equal to lambda x, right? So what we can say from here that for any natural number n, k equal to 0 to n, ak a to the power k x, or the same x, okay, eigenvector x. What is this? This is the summation ak lambda to the power k x equal to 0 to n for any natural number n, right? But now we know, so this x is just a fixed vector, so I can write it in this way also. Right? So since the right hand side here, so not the, so this is equal, these two things are equal, and we know that this series divergent, this series is divergent because of the fact, because of the given fact that for this series, this is the radius of convergence. So we know that whenever mod z is greater than r, this series is divergent. So clearly here the right hand side is divergent, right? So this is divergent because mod lambda is greater than r. But if this is divergent, this implies that this is divergent. Okay, so we know when such a series is convergent, when rho a is less than r, and when is divergent, when rho a is greater than r. All right, so there is also one more result I wanted to mention. So I'll now give this as an exercise. So this is actually this follows because of this result as we have obtained here. These are like simple observation, or you can say the consequences of this result, that these quantities here make sense. Similarly, you can prove this result also. So as a corollary of this result, you can say that if we have a matrix A, So if we have a matrix A, and if row A is less than 1, row A is less than 1, then clearly I minus A is invertible. This I have already given you one exercise why I minus A is invertible if row A is this. But not only that, you can say that the inverse of I minus A is actually this series. Now you can tell, you can easily, because of that exercise which I gave you at the beginning, you can see why I minus A is invertible. Once it is invertible, you can show that the inverse is actually equal to this. So I will just mention why this part is true quickly, or I'll give you just hint of the proof of this part. So you know what would be the radius of convergence of this series? Can you tell me the radius of convergence of this power series? What is the radius of convergence of this series?
1.
Is 1. Okay, so the radius here, the radius of convergence here is 1. And therefore, from the previous result, we know that a to the power k equal to 0 infinity, this exists. This limit exists. So let us call this limit as b. Okay. Now we want to show that this b is actually inverse of I minus a. Right. Now this follows because if you do this I minus a, multiply this with this summation k equal to 0 to n for any natural number n. If you multiply it with this, so then this is just I minus a to the power n plus 1. So when n tends to infinity, you can see that I minus a, this term is just b is equal to I. So that means b is the inverse of I minus a. Okay. So now, so it's time, so we can stop here. But now at least we have answered whatever we wanted to answer using this norm. And this now gives us different ways. At least now you know, whenever you say exponential of a matrix or cos of matrix or sine of a matrix A, or when you say a series of matrices is a series in matrices is convergent, I mean the power series is convergent, you know now a way to say when it is convergent. Okay, so now in linear algebra there is a different, like if I want to take more lectures on these, then I can do that by giving you what are the properties of exponential of a, or what are the properties of like trigonometric functions in a matrix, like cos of a, sine of a, for example. Now there are a lot of questions you can ask, and then some of the questions are true, but some of the questions you might not answer without any assumption. For example, as I mentioned, this cos of a you can always define for any matrix A, square matrix A. But then you can say, okay, what about cos a plus b? Okay, this is also defined, but can you say that cos of a plus b is equal to cos of a, cos of b minus sine of a, sine of b? This is true when a and b are scalars, but it is true when a and b are matrices. Is it also true? So this kind of questions you can impose. In fact, this is not true. You can define, the left hand side is well defined here. The right hand side also you can define by doing some calculation in the by multiplying two power series. This is also defined, but whether the left hand side is equal to the right hand side, that is the question. And in general, this is not true. There has to be some condition, and for example, for this particular case, if a and b both commute, if ab is equal to ba, then only this kind of thing is true, this kind of result is true. So similar way, you can impose other questions also, like whatever you know for exponential or trigonometric functions, or some other things you can define using the power series in matrices, and then you can see whether what results you know for scalar or for usual power series in real numbers or of real numbers or complex number. can we have similar like formulation for matrices also. Okay, so this give you like different like sections to read, to study. But we won't focus or we won't go in details of this thing. But if those who are interested, they can explore this. Okay, so in the next class, so I'll just define one thing here based on norm, which I wanted to define just to conclude this chapter. I'll take only 2 minutes or maybe 5 minutes in the next class, and then we will define or we will start matrix factorization. So there are some nice matrix factorization, 4-5 type of matrix factorization, which gives you a different way to look at a matrix, a given matrix. So we will start in the next class, we will start matrix factorization. And as I mentioned, the next class I will start at 3 p.m. and it would be on 2 hours just to make up for the half an hour we lost in the previous class. Okay, so the next class would be from 3 to 5. I will send you a reminder and also an invitation for that. So we stop here. If you have any doubt or any question, you can ask.
हेलो सर.
Yes.
सर एक्चुअली 2 से 3:30 तक कॉम्प्लेक्स की क्लास होती है.
2 से 3:30 तक क्लास होती है थर्सडे को.
यस सर.
और हाउ अबाउट मंडे?
यस सर, मंडे को भी.
और फिर 5 बजे से भी क्लास होती है आप लोगों की? मतलब कुछ लोगों की होती है एटलीस्ट.
हाँ हाँ, कुछ लोगों की होती है सर.
So how many? So Saurav, you are in PhD or what? MSc?
नो सर, एमएससी.
MSc. So since most of you are from MSc and you have class from 2 to 3:30, so for those who are like in like MTech or in PhD, so I will take a class from 3:30 to 5:30, the next class, and the last half an hour you please look at the recording, because otherwise I won't get a free slot. You please look at the recording. If you have any doubt, I can take that class, that half an hour again if you want. But for the time being, I will take a class 3:30 to 5:30. The next class would be 3:30 to 5:30. And the last half an hour, you can look at the recording if you want. I will provide you the notes as usual. But if you have any doubt, if you still have any doubt, you can ask me, or if you want, I can take that half an hour again sometime later. So the next class would be 3:30 to 5:30. So we can stop now. Thank you.
ओके.